Professor R. Ashokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tambaram, Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series in applied electronics. We have been going through a course of lectures on defects of images. This lecture is intended for the 4th semester students who are doing applied electronics. This particular topic comes under the paper Basic Physics 2, and we have been going through what is called chromatic aberration, which is one of the defects. As I told you in the previous lecture, if you have a convex lens and if white light is made to be incident, then it will lead to a colored image, and the contents of this lecture, that is the lecture number 8, or lens maker's formula, expression for longitudinal chromatic aberration, condition for achromatism of 2 lenses placed in contact, achromatic combination. What is chromatic aberration? As I told you in the earlier lectures, when white light is made to be incident on a spherical lens as shown here, it is made to pass through a spherical lens, then the white light will be getting dispersed. It is because of the fact a lens, a convex lens can be thought of as if it is made up of number of prisms. You know very well, when white light is passing through a prism, you will be getting dispersion. What is dispersion? White light getting split up into different colors in the order of Vibgyor. And similarly, here also you find the blue or violet coming to a focus here, and a point to be noted is, for the white light you do not get a single focal point, all the light rays do not come to a single focal point, because the white light consists of different wavelengths. So, white light it is getting split up into different colors and they are getting focused at different points. Blue is coming here, or violet will be coming here, green is here, red is here, and so on, right. And because of this defect, the so called chromatic aberration, what is the problem you have? Supposing you catch this the image of an object. What is the object? The object is here. You got a building, a beautiful building, but when this beautiful building is seen through a lens, the image that you catch using your camera, image that you get is looking like this. What is the difference between this image and this image? This is the original object, and the building that you have here, when you get through a camera which is having a lens, because of the defect in the lens, that means It is inherent, it is not, the material is not defective, right. It is inherent property. Why the defective image is obtained is the physics behind it is the one that we have to understand. What is the problem that you have? You see at the edge you see note the difference between this edge and this edge. So, the image that you get here, you have some coloration, right. You got a violet light here, this looks like violet, and then look at the columns, the vertical columns that you have got here. Okay. Now, they are appearing to be somewhat colored, not only colored, slightly bent, right. So, all this deformation that you get in the image is due to what is called chromatic aberration. This is the best possible way in which chromatic aberration can be explained. You take a fine building and get the image using a lens. Because of the inherent problems with the lens, you get the defect known as chromatic aberration, and this defect can be minimized by using what are called achromatic lenses. I will come to that later, but a single lens will lead to this kind of aberration. What is aberration? It is a defect. Instead of getting the real image, the image that you get is blurred or getting colored. This kind of coloration that you get using a single lens is known as chromatic aberration. Now, we go through what is called a lens maker's formula. Now, when you make a lens, a convex lens, the radii of curvatures of the two surfaces will not be equal. You have here R1. What is R1? R1 is you have this surface, when you come, this is a part of a circle or in 3 dimensions part of a sphere, right. So, you can complete it. Okay. You have a circle here, and this will be the center of circle. Similarly, there will be for this surface again forms part of a circle or a sphere in 3 dimensions, right. Okay. For this will be the center. So, for this surface R 2 will be the radius of curvature, whereas for this surface of the lens R 1 will be the radius of curvature, right. Now, I hope you understand, for this surface it is a part of a circle, right, whose radius, you got a circle, the radius will be R 1 from here to here or from here to anywhere, because the circle from this center to any part of the circle, right, that will be R 1, right, that should be constant. Similarly, from here for this circle, from the center of the circle to any point on the circumference of the circle will be R 2. Okay. What is R 2? R 2 is the radius of curvature of this surface. So, the lens has got two surfaces. This surface has got a radius of curvature R 2, whereas this has the radius of curvature R 1, and the thickness of the lens is d. What is f? F is the f, as you know, is the focal length, right. When you got a light beam passing through a convex lens, the light beam will come to a focus. Now, all of you, when you are young, small children, they go out with a lens and use the sunlight to burn paper or film or something, and because you show the white light will come to a focus, right. When you are made to make the white light to pass through a lens, it will be getting focused and a lot of heat will be generated. So, that the paper can be burnt, and that point is nothing but the focal point, right. This is a focal point, right. When light rays are incident, they will be getting focused here, right, the focal point. At that point, the temperature will be very high. This is the so called lens maker's formula. As far as we are concerned with respect to defects of images, let us move forward, and you can have for a lens of thickness d, the thickness d here, then the focal length can be related to R1 and R2 using this formula, and this formula is known as the lens maker's formula, which goes as follows: 1 by f will be equal to n minus 1 into 1 by R1 minus 1 by R2, where R1 and R2 are the radii of curvatures. R1 is the radius of curvature of the lens surface closest to the light source. Okay, where is R1? Where the source is here, you see the the light is coming here. So, for this is the surface, right, this surface. Okay. For this surface, what is the radius of curvature? This is R2. For this source that you got here, the nearest to the lens means we are referring to this surface. So, this surface has got a radius of curvature R1, right. This surface has got a radius of curvature R1. This is the radius of curvature which is being referred to here. R1 is the radius of curvature of the lens surface closest to the light source, whereas R2 is the radius of curvature of the lens surface farther from the light source, and d is the thickness of the lens, n is the refractive index, and f is the focal length. So, this formula shows that the focal length depends upon the refractive index. The refractive index is the one that depends upon lambda. That will make you what? The focal length becomes a function of lambda, right. The focal length becomes a function of lambda. That is the reason why you got different focal points, right. You got white light, the focal point for blue is here, red is here. It is because of the using the lens maker's formula, you can argue or you can explain why you got the different colors coming to a focus at different points. For the simple reason, the focal length will depend upon the colors. So, for violet I will write f v, for red I will write f suffix r. Okay. So, this chromatic aberration, it is only present in lenses. Mirrors obviously have no chromatic aberration, because they operate by reflection rather than refraction. The most noticeable effect of chromatic aberration is that images of objects illuminated by white light shows colored bands around the edges, because of the different colors in the white light are getting focused at different points in the image plane. This effect is in addition to all the other aberrations, about different aberrations. Now, I mentioning about the colored bands, these are the colored bands, right, because the white light is getting split up into different colors. So, remember, chromatic aberration is the defect caused when white light is incident, not a monochromatic beam. When white light, which is composed of different colors starting from violet to red, only when white light is incident or when it is made to pass through a lens, then you will be getting this kind of coloration and all these things, that gives rise to so called chromatic aberration. That is what I am talking about here. So, different colors are there in the white light. So, they are getting focused at different points and in the image plane, and the coloration occurs, right. White light shows colored bands, and this defect, as I told you, the so called chromatic aberration. I can try to combine a lens of this kind. I have them, you see two lenses, right. One is made up of crown glass, the other is made up of flint glass. Now, what happens? Now, unlike the earlier case wherein the violet came to a focus at a point here, the blue is coming to a focus here, or violet would have come here and red comes here, they are getting focused at different points. Instead of that, this can be minimized, but here it is shown as if it is completely eliminated, but the point is you can try to minimize by combining a crown glass with a flint glass. Why do you use crown and flint? They have different refractive indices. The refractive index of crown will be different from that of flint, and once again you are making use of lenses. You are using earlier a single lens. Now, whatever defect that is caused by the convex lens is eliminated, is reduced by combining the convex lens. This is the convex lens that you have got here, right. This is the convex lens, and you combine and you have the biconcave lens. You got a lens here, right, combined with this system, right. You got a crown glass, flint glass, and these two are made use of to make the light beams of different colors to get focused at the same point. See, the violet comes to focus at the same point, red also is getting focused at the same point. Thereby, the defect that you had earlier, the chromatic aberration is eliminated, but of course, in principle it cannot be eliminated. This is an exaggerated thing, it can be minimized, and the same thing I will show once again. So, different types of glasses, as I told you, you can combine crown glass and a flint glass, and you can try to get a single focal point. This is what we are trying to get, right, a single focal point by combining so called flint and I mean not only flint and crown, but also lenses of different kinds, a convex and biconcave lens, that gives rise to a single focal point. As you will see in the figure to come, this is a picture that you have to carefully observe. The point I want to make is the following: the blurring that I am talking about, right. What is blurring? That is green comes to focus here. Where is violet? You see here carefully, violet is getting focused here, green is getting focused here, okay. Red is getting focused on the screen. So, the blurring is 0.30 millimeter. Okay. So, the image axial chromatic aberration, but a lateral chromatic aberration, right. You get the images getting focused here, and green coming to focus here, and red is found here. The blurring that you got here is this is the magnitude that is shown here, 0.30 millimeter. So, axial chromatic aberration, you got a single lens, right. On the other hand, if you use a chromatic doublet, right, you see two lenses, you got a combination of two lenses, right. You got a lens here and another lens here. If you combine two lenses, then the blurring is reduced from 0.3 millimeter to 0.01 millimeter. Note that it is not completely eliminated, right. The blurring is not completely eliminated by combining two lenses, it can only be minimized. The blurring that you got for 0.3 millimeter is reduced to 0.01 millimeter, the magnitude is reduced. So, I would like to underline, note that the chromatic aberration is not completely eliminated when you combine two lenses. So, what I would like to state is, you should understand what is meant by achromatic combination. An achromatic combination is nothing but a convex lens being combined with a biconcave lens. These two can be combined, and remember, these are two lenses made up of different materials, a convex and biconcave combined together, and one is made up of crown, the other is made up of flint. Thereby, the blurring of the image that you obtain is minimized or reduced to the maximum extent. The magnitude as shown here, blurring is 0.30 when you use a single lens, but when you combine two lenses, that is called a achromatic doublet, the blurring is reduced from 0.3 to 0.01 millimeter. This should be borne in mind, this is important thing. So, now we will pass on to obtain the mathematical expression for the longitudinal chromatic aberration. You know what I mean by longitudinal chromatic aberration. This is a I started from here, and this is the longitudinal, right, from when the violet comes to a focus here, somewhere here, blue will here. Where is blue? Violet, blue, green, bluish green, then yellow and red. You got in VibGR, V stands for violet, R stands for red, G stands for green, and so on, right. So, one has to start from violet. So, violet will be here, and blue is here, green is here, red is here, and from this point to this point, from here to blue, it is F B. Violet will be somewhere here. So, that is F B, F suffix B. That is the focal length that is obtained for violet light. Focal length obtained for red light will be F suffix R. With these notations in mind, let me now start to obtain the expression for the longitudinal. This is called a longitudinal chromatic aberration. Okay. So, we will have here, when a parallel beam of light, white light, is made to pass through a lens, the beam gets dispersed and the rays of light of different colors, I mean the wavelengths, they come to focus at different points along the x axis. As I showed just now, the violet rays come to a focus at a point nearer to the lens, whereas the red will be far off, right. The red rays of light, they are focused at a farther point. So, as I mentioned earlier, F V is the focus for the violet rays, and F R, what F R is the focal length for the red line, I mean the red light. F R is the focal length for the red light, because or the red light is focused at a far off point, violet is getting focused at a nearer point. So, the distance that separates from the center of the lens to the focal point of violet is F V, from the center of the lens to the point where the red is coming to focus is called the F R. The colors in between the violet and red come to focus between, obviously between F V and F R. The distance F V minus F R, right, this is important. The distance F R minus F V, or whatever be the thing, that difference between F V and F R is called x, that is the magnitude of the longitudinal or axial chromatic aberration. So, the value of x is to be deduced mathematically. Let me now summarize what I told you in today's lecture, that is lecture number 8. The lens maker's formula gives a relation which connects the focal length, the refractive index, and the radii of curvatures of the lens surfaces, right. You have got two surfaces, R1, R2. The second point is the longitudinal chromatic aberration is nothing but the distance which separates the focal points due to violet, namely F V, and the point where the red light is getting focused, namely F R. This gives the so called longitudinal chromatic aberration. Let me ask you the questions, because would like to know of what you understood from today's lecture. And so, the questions are as follows: what is lens maker's formula? What is meant by longitudinal chromatic aberration? What kind of lenses which are used on, and what materials are used to produce achromatic combination? With this, we come to the end of today's lecture, and the rest of the things like the expression which is to be obtained for the longitudinal chromatic aberration will be taken up with the lectures to come. Thank you.